Okay, so I'll start by introducing you, Laurie. So we're delighted to have with us Professor Laurie Wilcox today in our seminar. Laurie is a professor of psychology. She did a BSc in psychology at the University of New Brunswick, and then an MSc and PhD at the University of Western Ontario under the supervision of Brian Timley. She then continued to a postdoc at McGill University in Montreal. Then she joined York University and holds a cross appointment in the graduate program in biology. She's also a long-standing member of the Center of Vision Research at York University. Laurie holds a Tier 1 York Research Chair in 3D Vision, is a fellow of the Association of Psychological Science, and is the outgoing president of the Vision Sciences Society, which she's also on the board of its directors for more than 4 years now. She supervised dozens of students and published many papers. Wilcox is the head of the 3D perception and psychophysics lab at York University. She uses psychophysics to reveal properties of the neural mechanisms that underpin and afford stereoscopic depth perception, also combining depth from stereopsis and other sources of information. She also investigates how and when stereoscopic depth information is used in more complex environments, including virtual and physical ones. She also has a long history of collaboration with the industry, including in 3D film and displays like IMAX and Christie Digital, and more recently in virtual and augmented reality like Qualcomm and image quality with Video Electronics Standards Association, also known as VESA. So we welcome, Laurie, you to our seminar today. We'd be delighted to hear about your research today, and thanks so much for joining us.
Okay, I'm going to share my screen. As Eileen pointed out one time at a meeting, this is the time when everybody talks to themselves when they start sharing their screens, which I love that. Thanks so much for the introduction, Sharon. That it's interesting sitting and hearing about yourself. It's like, did I do that? I don't know. It's a pleasure to be here today and to be part of your speaker series. A quite impressive speaker series, I got to add. So I'll jump right in, and I'll start off by stating something which is really obvious, and that is perceived depth depends on many factors. And some of these are very low level, like timing and contrast. And others are mid-level things, like we've done work showing the impact of perceptual organization on depth from binocular disparity. And there's also the availability and consistency of multiple sources of depth information. And this last one is experience. And I decided that today I would kind of go out on a limb and focus on experience. And this is not something that I normally talk about with respect to my work or focus on, but what I've done is I'm going to try and take a slice through a number of different experiments where we have very significant, compelling effects of experience and try to put that forward for you to consider, and I'll make an effort to come to some useful conclusions, but I can't promise I will, but I'm trying. So I've clustered the work in two categories: long-term effects of experience, or long-term experience and the effects on depth perception. And within that category, I'll start off by talking about experiments where we study how we see depth from binocular disparity in the absence of other depth cues. And then I'll go on to talk about depth judgment, some depth judgments in more complex environments where the experience is long-term because it's part of their job. So with aircrew and with the 3D film industry. And if there's time, I'll then wrap up with an experiment, a more recent series of experiments where we found really quite dramatic effects of short-term experience. So test order within a study. And feel free to interrupt me at any time. Just start talking, ask me questions. I don't mind at all. In fact, it helps me to, slow down my roll a bit if you interrupt me. So feel free. Okay. So let's start with, hold on, I'm jumping ahead here. Long-term experience, the study where my PhD student and I, Brittany, looked at depth estimates for using binocular disparity in relatively simple isolated stimuli. Okay, so the original aim of this study was to compare depth magnitude assessment methods. It's quite a simple, straightforward experiment where we compared 3 types of assessment, one that was within the visual modality, where we just had people adjust a horizontal ruler or line to indicate how much depth they saw between a pair of lines. And then the other 2 were intermodal, anyways, where they had to use their hands to estimate the amount of depth. And in one case with the digital caliper, they did this free form. They just put their thumb and forefinger down on the table. And in the other case, we're using our haptic sensor strip, where you put your thumb against the base and then press down along the strip to indicate how much depth you see. And critically, we use 2 groups of observers, a group of very experienced lab members and a group of, shall we say, novices, the undergrad novices who hadn't had any experience with these types of tasks. The task was, as I said, very simple. We had 2 lines. They were displayed in a mirror stereoscope, and the stimulus was always the same. So the comparison across methods was a reasonable one. We displaced 1 line in depth. That's simulated here. And observers indicated how much depth they perceived. And we tested a range of disparities. So I'll start with the results from our experienced observers. And I'm plotting the data in this way throughout, with the estimated depth on the vertical axis in millimeters, and then the theoretically predicted depth from the offset on the horizontal axis. And if they were performing perfectly, they would fall along this line. So for our experienced observers, using the haptic sensor strip, we found that—
Laurie, could I just get a point? Sure. This number is going to depend on viewing distance. Yep. Was that unambiguous in the setup?
So this is in a stereoscope. So they were viewing, the stereoscope was set up so that the vergence was correct for the distance of the displays. So does that answer your question?
I guess so. So,
yep.
I mean, you didn't say anything about fixation or anything, but there's the line is set up with so that the vergence on the non-moving line determines the overall viewing distance.
Yeah, so yeah, I skipped over some details, all just to try and move things along. But in fact, there was a fixation that appeared so that they knew where they were fixating. They maintained their vergence on that spot, and then the stimulus appeared. They made their judgment, and then they refixated and moved through trials. Yeah.
Okay, sorry to slow things up.
No, that's totally fine. And in fact, like I said, I'm happy to do that. We can always chop stuff off at the end. I don't mind. Was there another question, or no? Okay. So these are the results for the haptic sensor strip. Here are the results for the digital caliper and the results for the virtual ruler. So the first thing you might notice is that we're getting very similar data across the 3 methods. So that's great. But also our experienced observers are very accurate, and their depth estimates are pretty much falling along the theoretically predicted line, which again is great. But of course, as you might expect, the results from the inexperienced observers differed. So I'm showing the data in the exact same format. And now we're dealing with our inexperienced observer results. Here are the data from the haptic sensor strip, digital caliper, and the virtual ruler. So the good news was that, that the three methods they were able to use the three techniques equally well, but you can see that there is a very substantial change in the slope of these data, where we have overestimates at the low end and substantial underestimates in perceived depth at the larger offsets. So this really was striking to us. I mean, we were familiar with the underestimates occurring, but the difference between the experienced and the naive group was quite interesting. And of course, when we asked why, the first thing we turned to is whether or not this was caused by conflicts between stereopsis and monocular depth cues within the stereoscopically displayed stimuli. And to be clear, because we just presented these isolated lines, and if they move their head, there'd be conflicts with motion parallax. They were always accommodating on the screen plane, so that's a potential source of conflict. We didn't adjust the size of the lines, so also perspective foreshortening was inconsistent. So to assess whether or not as a aggregate, these Q conflicts might be responsible for the difference, we replicated this study under what we would call perfectly consistent conditions, that is with the physical stimuli. And we did this using our physical test environment. And let's see, I think, there we go, where we have this series of motion stages arranged. So we have control over stimuli. We can present them within this space, pretty much anywhere within a 1 meter by 1 meter space. The observer sits at this end and makes their responses using either a gamepad or the haptic sensor strip in this case. And we control presentation time by controlling the lighting. And we recreated the stimuli, so they had the same dimensions, the same viewing distance, all the important aspects of the stimuli were the same in the virtual environment. And then, so the hypothesis was, of course, that if these naive observers' bias was due to the Q conflicts or even the absence of some of the depth information in our displays, then they should be much more accurate in the physical environment. So here are the results from the physical experiment, where I'm again plotting the data in the same manner with the actual versus the estimated versus the actual. And here's perfect performance theoretically predicted. Our experienced observers are the same group of experienced observers that we tested throughout. So as you can expect, you might expect they're doing very well on this task. We tested a new group of inexperienced observers, and we found that unlike the previous experiment, they performed perfectly, pretty much. And the results were statistically indistinguishable from that of our experienced observers. So that confirmed to us that there's something very, very critical about the nature of the additional depth information. Hold on, I'll move here. So that using the virtual stimuli, the inexperienced observers make large systematic errors, but the experts don't. And for both groups, performance, of course, with the physical targets was highly accurate. And the deficits that we see that from these novices in our virtual environments, I just want to highlight that that could be due to the lack of supportive depth information, because we had isolated stereopsis from other depth cues, but it can also be due to the conflicts between binocular and monocular depth information. But regardless, I think the point with respect to experience here is that the expert observers are able to, in the virtual setting, attend to binocular disparity and to disregard either the cue conflicts, or they can use binocular disparity on their own. So they've learned something quite specific here.
Laurie, may I ask a question?
Sure.
I wanted to ask, you're saying that they were experts, and I wanted to ask how did they acquire their expertise? Were they experts specifically in these tasks in the lab, or did they have some profession, or in what way?
Yeah, that's a good point. And I use the term expert kind of loosely here. These are people who have participated in numerous psychophysical studies of stereopsis. So these are people, I don't have an explicit definition or criteria for expert, but they have consistently very low thresholds, and they're reliably able to do this. And they've had lots of time, lots of experience with 3D displays in the lab, specifically stereoscopes in this case. Yeah.
Okay, thank you.
Yeah, in this case, I'm using the term experts to refer to people in the lab, scientists who've done stereo experiments. But in the next case, in the next one, the experts are actually experts in different domains. So in this next series of experiments, there are the two examples of long-term experience that I wanted to tell you about. And I apologize to anybody who I've explained or I've told the aircrew, where I've talked about the aircrew data already, so it may seem kind of redundant, but it fits. So I think, and it's interesting enough here. So the background for this study was that the Royal Canadian Air Force, it assesses stereo acuity, but it has no requirement for it. So recruits don't have to meet some minimum level of stereo ability. But the US Air Force does have a requirement for stereo acuity of 40 arc seconds. So this forms an exclusion criteria for the US Air Force. And this difference between the two air forces is important because Royal Canadian Air Force pilots and aircrew will go down to the US to train. If they don't meet the criteria for flying aircraft in the US, then they're not allowed to do the training. They get sent back. So this is an issue for the Royal Canadian Air Force. And what they asked is whether or not such an exclusion criteria is necessary. They're reluctant to add exclusion criteria because, unlike the US, Canada doesn't seem to have a lot of young men who want to be fighter pilots. And so they're reluctant to rule out the recruits, whereas the US, they've got tons of people who want to be fighter pilots, so they have no trouble with extra exclusion criteria. So our goal, the project goal that we had, was to identify and evaluate conditions where binocular vision was operationally relevant for aircrew. And we honed in on a few tasks, but the one I'm going to tell you about is altitude estimation for maintaining low hover. And low hover, and this is particular to helicopters, of course. Within a low hover maneuver, the flight engineer, who's the person that usually sits at the back here looking out and does call outs to the pilot to help them maintain a specific distance from the ground plane, or to tell them how close they are or if there are obstacles. So they must keep the helicopter at a fixed height relative to the ground so that they can let people in and out, basically. And they call those extraction and insertion maneuvers. And we figured that binocular vision would provide them an advantage in this scenario. And here's an example of a pilot who is maintaining a low hover. And I'm showing you this because it's remarkable how stable that helicopter is and how close it is to the ground. It's probably only at about 1.5 feet above the ground. And they tell us that this is one of the hardest maneuvers that they do to keep that so stable. And yes, and I've told this story before, but the first time I showed this video in a talk, Wendy Adams put her hand up and said, but what I want to know is how are they fitting so many men into that helicopter? Ha ha ha. Okay, which I thought was hilarious. Okay, so we simulated this. Let me just, and I've got a cartoon here showing it. We simulated this in a lab setting where we have an individual, an observer, sitting on a chair on a platform that would raise them to the height, the same height that the flight engineer would normally be sitting, looking out the side of the helicopter, same angle, and at the same distance from the simulated skid, which you can see here. So that's about 6.5 feet. And you can see that the skid protrudes out here because we actually put a piece of PVC piping to extend from the displayed skid that was in the scene to make it have a little more, it seemed more realistic. So on this display, this is a 4K 3D plasma display. The observer is viewing different ground planes, and they're going to be estimating the distance between the skid and the ground plane. And it's a stereoscopic display. That's why they're wearing those glasses. So we used a magnitude estimation procedure where observers assigned a value, just whatever value they wanted, to the distance between themselves and the skid. So let's say they chose a value of 10. And then they use that value to then indicate the distance between the skid and the ground plane. So if they had said 10 and they thought the distance to the skid from the skid to the ground plane was half that, they would give that a value of 5. And then we tested a range of distances between the simulated ground plane and the skid over a range of 0 to 5 feet. We tested both monocularly and binocularly. We tested our inexperienced undergrads, this little guy that you see here, and we tested a group of aircrew. As you can see now, he's wearing his hat. I'll do that again because that's fun. We had 31 people in each of these groups, and that was quite an achievement for us getting our these aircrew, such a large group of aircrew. It was really good of them as well to take the time to participate. So the stimuli were, we had these simulated ground planes. They were very high resolution. You can't really tell that here in these little thumbnails. We had 3 of them. The grass, stones, and runway textures contained both 2D and binocular cues to depth. And I'll note that the plane recedes in depth on an angle consistent with the angle that the viewer is sitting. So it's basically slanted off in depth. The runway has this yellow line. To avoid people using that to make their distance estimates, we varied the width of it randomly, and we told people we were doing that and that they couldn't use it. The grid pattern is an important one because a grid is scale invariant, which means that it doesn't have any monocular information and only would contain stereoscopic depth information. So this should be hopefully clear to everybody, and we can jump right into the data. So what I'm going to do is show you the monocular data for the two groups first. And I'll plot them in this manner with the estimated altitude as a function of the simulated altitude. And the data that I've got shown, that I'm showing here now, is for our grid pattern, which, because it's monocular, doesn't have any, doesn't change in its slope with simulated altitude, which is a reassuring thing because it shouldn't. But instead, observers just kind of pick a distance and then and go with it for all altitudes. But for our remaining textures, the green is the grass, the purple is the stones, and the teal is the runway. You can see that these monocular textures show very slight increases with simulated altitude, but substantially underestimated at this end, at the larger altitudes, and a slight overestimate at the smaller or lower altitudes. So very shallow slopes here. What about our aircrew? They show the exact same pattern of results for the grid, which again was reassuring. But what we found was with our other textures that the aircrew showed a significantly higher slope for all three of the ground planes. So they were much better able to use the monocular depth information to make these depth judgments, these altitude judgments. Okay, so hold on to that point. And we'll move to the binocular data. Now, in the binocular condition, the grid, which is shown here, does have disparity, and clearly the inexperienced observers are able to use it, but they're not performing at predicted levels. So they're showing a much shallower slope when they're using binocular disparity on its own. However, when you add in the other monocular depth information that's available in our other textures, you can see that they get pretty good depth scaling. That is, they're increasing their altitude estimates with the increase in simulated altitude. How about our aircrew? Well, it turns out that for the aircrew in the binocular test condition, the data are virtually identical to our inexperienced observers. So you can see this in the grid data shown here. And then with all the other texture information added, there was no significant difference between our inexperienced observers and the aircrew on the binocular task. Does anybody have any questions about this data, or before I scoot to my conclusion about this?
Laurie, your air crew, are they the actual helicopter flight engineers or the generic air crew?
No, so these, we had a collection of pilots and flight engineers.
But they flew helicopters in the kind of operation that you're simulating? Yep. Okay.
Yeah, it was a real achievement to get them. And what I would have loved to have done is just had this large group of flight engineers, because they're the ones that are constantly making those depth judgments. They're the ones that are looking out the side of the aircraft, but it's hard to get them. Okay. So yeah, I think we had a few of them, and we couldn't call them back in again. So yeah. But,
hi, Laurie.
Brian, hi.
Hi. You talk about it as being the disparity information in the binocular condition, but in a sense, it's really an absolute judgment task, isn't it? So you're really relying, if you like, on convergence rather than disparities per se.
Well, actually, in this we've done a couple of experiments looking at altitude estimation, and in this task, we believe it's a relative disparity. It's a relative judgment, because they report that they judge the distance relative to the skid. So they're constantly comparing the distance, the ground plane to the skid. So if they were just looking at landing, say the distance to the ground plane, that would be the absolute distance. But yeah, that was why we honed in on this one.
Okay. Mm-hmm.
Yeah. But when we did do absolute altitude judgments, so where they do call outs when they're landing, we found that there was just, yeah, there's no effective stereo, as you might expect.
Okay.
But yeah, I know I have that bias, so correct me all the time that I think about binocular vision and I just immediately go to stereo, but I am fully aware that vergence is important too. Okay, so let me move to my take homes here. This is the interesting bit. The air crew showed a monocular advantage in our simulation relative to our novices. The judgments based on binocular depth cues were indistinguishable between those two groups. And that the advantage that the air crew had was not therefore simply due to their experience making depth judgments, but somehow reflects their specific training. And when we interviewed them and talked to them about what they did in their job, they always reported specifically being trained to use 2D depth information for landing, for whether they were doing low hover or whether they were landing, for instance, the size of trees in the area or the shape and scale of ground terrain. So then that's, in some ways, I mean, it's anecdotal, but it's clear that they are trained to use this monocular information. And as a result, even in our simple simulation, they do show this advantage in using the monocular depth cues that we had in those scenes. So the training and the experience they have is having very specific effects on how they use depth information. Okay. So I'm moving to another long-term training part. This experiment was part of a collaboration that Rob Allison and I had with 3D filmmakers. We were part of a consortium, 3D Flick, it was called. And it had both filmmakers, directors, scientists, and film industry folks. And as part of that, largely because we had access to people with expertise, specific expertise, we wanted to assess stereoscopic performance as a function of expertise. And so, and we wanted to take a careful look at what the important factors were. So we recruited 11 observers into each of 4 categories. We had a group of 3D film editors, composite artists and animators. And these were people who basically worked on 3D material all the time, every day. Then we had our group of stereoscopic vision experts. And those are lab people who have had their 10,000 hours of psychophysics on a stereoscope. We included a group of vision science experts who are very familiar with displays and psychophysics, but were 3D novices. So they didn't have the 3D experience. And then we have our undergrads, our inexperienced novices. So we have these 4 groups, and we screened everybody for visual acuity and for stereopsis. So everyone had, I think our criteria was 40 arc seconds. We used a mirror stereoscope and the same tasks for everyone. We did a depth discrimination, a disparity matching, and we tested their fusional range. So how large a disparity can they fuse? So, and the stimulus was very simple. just a fusional frame of dots, and they were asked to make judgments about the little line in the center, and if you can free fuse, which I'm sure Brian and Julie and lots of people can here. You can see it in the stereo pair below. I'm going to jump right to the results. These are the results for the fusion limit. And what you can see is there were absolutely no differences in our groups in the maximum disparity that they could fuse. Let's see. And then, well, missed there. Our disparity matching data showed absolutely no differences between our three groups, except right here at the largest disparity. And I guess I haven't described the task. In the disparity matching, they're just adjusting a probe to match the disparity of a visible target. And we expected people to be quite good at this. So, but we thought we might see some differences. We didn't even really see differences in the variability here. Where we did see a difference was in the discrimination thresholds, which is what you might have expected. But the pattern was somewhat surprising. So we found that our industry experts and our inexperienced observers performed identically pretty much on this task. So our industry experts are our 3D. These are people that are working with stereo all the time. Yeah, however, the only group that showed any real advantage was our stereo experts. And these stereo experts, the lab people, had very low thresholds, very low variability. The vision scientists look like they're getting down there, so there's some benefit to knowing how to looking at displays and doing psychophysics, but this difference wasn't statistically different. So this is what surprised us quite a bit. We anticipated seeing something different here, and yeah, we can talk about why this is. It's largely that they're not making depth discrimination judgments all day. They're looking at super threshold imagery. But anyhow, let me recap here.
But just to be clear,
yeah.
Laurie,
yes,
none of these tasks bear much relation to the depth judgments that were in the first part of your talk.
Yeah, that's right. And I so wish that I had back at that time. So that experiment we did in 2013, I wasn't doing as much depth magnitude estimation. And I really wish that I had included that kind of task there, because I think that might have shown a bit more of a difference. But yes, that's a very good point. So yes, surprisingly few differences between our groups. The stereoscopic 3D industry experts data was not different from the inexperienced novices on any of the measures, and only our vision scientists showed advantages, but only in the discrimination thresholds. And our stereo experts had the lowest thresholds. So that doesn't simply reflect experience with psychophysics, obviously, but that experience helps, it seems. So the improvements that are due to training or experience repeatedly seem to be highly focused and task dependent, even when they're doing this in the real world, under real world scenarios. That would be the take home from this. There's the training and the benefits that we're seeing are very focused, and that echoes the results of the aircrew experiment, where we did anticipate binocular advantages, not necessarily just binocular disparity, but we didn't see it because the benefits to the aircrew really were specific to the training that they got, which was on monocular depth information.
Laurie,
Yes.
The industry experts, they're always using moving images. Is that, do you think, why, in this kind of thing, they're not using stereo in the same way as you do when you're kind of judge things in movement?
So I think that's a really good point, Jan, and it's possible. But one of the things, our collaborators were all, we were working with a company that was an animation firm, a 3D, that dealt in 3D animation, and they often worked frame by frame. So they'd be looking at a frame and fixing, and compositing, and that was often done, with static images.
Yes, but the static images, when they're working frame by frame, is to indicate movement. It's not necessarily to indicate depth. It's to indicate depth in some circumstances. But
yeah, I see what you're saying. No, so these people were actually the stereo experts. So they were actually the ones that were supposed to be getting the depth right. There were other people that were getting it's incredibly divided and siloed. People that were just doing, okay, is this transitioning in depth? Is this at the right plane? Is this sitting on this surface? That kind of thing. So I thought they would show advantages. Yeah. Any other questions on this part? Because I'll move to the shorter term data. Okay, so this is a recent set of experiments that Brittany and I have submitted recently, and the experience in this case is short term, meaning within an experiment. And the experiment itself is focused on depth constancy and the occurrence of depth constancy in virtual and physical environments. So depth constancy, well, first of all, previous work, when there's lots of it, that has demonstrated in VR, distance is underestimated. It just happens over and over again. There's lots of evidence for that. And from that, we predict also poor depth constancy. And depth constancy being the ability to maintain a perceived interval in depth as being constant across changes in distance. So that's different from size constancy, right? So that's what we're used to. People walk away, they don't get smaller. So depth constancy is the interval in depth remaining the same as you move further away. And of course, if you have an object, depth constant, which has a certain volume, then depth constancy would mean that it has the same shape as it moves further away. So in this experiment, yeah.
Can I ask about depth constancy? Isn't it in some way very related to size constancy? Because it's like size constancy, you can think about it as being just one dimensional, or but depth is just taking that into 3D world.
Yes, yeah, they're very, very related concepts, and in fact, they can influence one another. But yes, that's true. They're very related. Okay. I just wanted to highlight it. Like if you had a pencil, and you've got it, you're holding it vertically, the size constancy is the size of the pencil in that dimension. But if you turned it around, the depth constancy would be the size of that depth interval in the depth dimension. I don't think that helped at all.
No, I understand. Thank you.
In this experiment, we assessed depth magnitude, again, in both real and virtual environments as a function of distance. And I've got an example of the type of stimulus we used here, if you can free fuse it. These are half cylinders, and they're textured with a pattern of random dots of different shades of gray. And for some reason, there's a delay on my end here. Oh, Okay, there we go. So our virtual test conditions were a stereoscope and an HMD. So we did both of these for a very specific reason, but I won't go into that here because we are limited in time. But yes, so we have our virtual test condition and we have a physical test condition. We use the physical test environment that I showed you earlier. Here's a top-down view on the top. You see the observer is sitting and looking through an aperture. The stimuli, as you can see here, are mounted on a big board. And these are the physical stimuli shown here, patterned with this, with the sheet of texture that we can replace. And they're mounted here with a magnet, so we can swap them out as well. And the stimuli can move along that motion stage. So we put it in position, the one we want to show, and then the lights flash on, and then the stimulus is visible, lights go off, and the observer makes their response. And we can, we had, I think, a set of 4 mounted on a big sheet, and then we could swap out the sheet in between halfway through the experiment. Importantly, we matched the virtual and physical stimuli for the luminance, the contrast, all of the geometric dimensions. We created them in Blender and then 3D printed the textures so that the texture patterns are the same. They're as identical as we could make them. Okay. And we tested 2 viewing distances. Again, I was saying that we were looking at depth constancy here. So we had a near and a far viewing distance. We had monocular and binocular viewing. I'm going to focus on the binocular data for these purposes. And we used our pressure sensitive strip, which we validated previously, to ask people to estimate the depth of the surface at its peak relative to the frame that surrounded it. And we were aware that we might see order effects, so we counterbalanced the physical versus the virtual test conditions. That's the important point for this talk. Okay, so here are the binocular data for, this is the aggregate data for our HMD. Again, I'm plotting the estimated depth as a function of the peak surface depth here, with the diagonal indicating perfect performance. Here are the results for the stereoscope, and here are the results for the physical stimuli. So when we got these data and we looked at them, we thought, wow, look at this. This is great depth scaling for in our virtual environments. The physical environment is showing very nice depth constancy, not so much in the virtual environments, but overall the accuracy was looking good. So, however, and this is the point, when you unpack these data and divide them in according to test order, you see a very different pattern of results. So here's what happens if the individuals did the virtual, one of the virtual conditions first, and it didn't matter which one. You see, here are the results for the HMD and for the stereoscope and for the physical test condition. So with the virtual experience first, you can see that there's the virtual data are less accurate. There's poorer scaling overall with the increasing surface depth and poor depth constancy. So basically on all 3 counts, we see this shallower slopes and a greater difference between the near, sorry, I should have said this. This is the near condition. This is the far condition. So the dashed line is always the far condition. And you can see in the physical, even in the physical test condition, that there's some loss in accuracy at the larger depths. There, according to the statistics, we still see depth constancy in the physical condition. You can see it's kind of slightly pulling apart, but there's no difference in the slope between these two lines.
Laurie, can I just interrupt?
Oh, of course, yeah.
You use the word constancy, but this isn't constancy in the sense that it doesn't matter at which distance you're viewing. You're using the word constancy that merely you get a linear relationship between the amount of depth. In other words, it scales up as you increase the disparity, which isn't really constancy, is it?
No, so constancy, I should be more careful about this. Constancy would be that you're seeing the exact same slope in these two. It wouldn't matter what the offset of that slope is from the vertical line, but that the slope of this and this should be the same. Right?
No, I don't think so. I think they should diverge in the way you've got them, but it's really whether, the extent of that divergence that reflects the, in other words, sorry, if you double the viewing distance, which then the disparities will go down by a factor of 4.
Right.
That's the constancy, isn't it?
Right. Yes. Thank you, Robert. Brian, thank you. Yeah, that's a good point. Yeah. So in this case, let me just bring this back. What we're seeing is with the virtual first test condition, we're getting a huge drop in the accuracy, and we don't see depth constancy in our HMD, in our virtual conditions. Now let me move to the physical first, because when we test the physical condition first, we see a much different, the pattern of results changes dramatically. And that is that the performance is much better in the HMD and the stereoscope and in the physical test condition. So the experience of having the physical test condition prior to the virtual test conditions has an enormous impact on the depth scaling. That's the take home from this. And we do see some overestimates here in the HMD data relative to the stereoscope. I should highlight that it was quite interesting that the results from the HMD and the stereoscope were so similar across all of our conditions, which is useful for people who want to use HMDs. But the impact of test order in this case, it was almost shocking to me. And I know that not everybody's as interested in depth, but you'd like to think that just by counterbalancing these things, you would get rid of any potential order effects. But in this case, you clearly have to consider these according to the test order. So just to recap, our virtual first observers, they had depth scaling and accuracy was poor in the virtual test conditions. They improved in the physical test condition, but it was still degraded. But when the physical condition was tested first, they showed very good scaling and accuracy in the physical test conditions, and performance was much better in the virtual test conditions, and depth scaled better with distance. And it's not clear what's driving this effect, and we've looked at a number of possibilities, including trivial ones, but it appears that the experience with the physical environment with all of this consistent distance and depth information, the information from vergence probably plays an important role here, then helps observers scale depth in the virtual space. And the reverse happens in the virtual first. But this is happening within an experiment. So this is not something that they're learning over time. This is a short-term situation-specific effect. Hold on. And in some ways, it echoes the results from the first study I talked about, where depth estimates were so accurate for physical stimuli for all observers. But seeing the virtual first condition degrades that, which was surprising to us. So anybody have comments or questions with this part?
I have a general comment, but if there's
Yes.
more to talk, I'll save it till later.
Okay, hold on. Then I'll just conclude and then we can chat. So, I mean, this kind of goes without saying that experience plays an important role in our ability to perceive depth and the depth information we use in both virtual and physical scenarios. Come on. There. That experience can be long or short term. And repeatedly, we see the effects of experience are highly specific. So stereo experts from the lab do very well with disparity-defined stimuli in the absence of other information or in conflict. Aircrew perform very well on 2D depth judgments, even when it's a simulation that really is very different from what they do in the real world. And short-term experience with a task determines subsequent depth scaling. But our untrained observers perform very well under cue-rich conditions, which they're used to experiencing in the natural world. So the results reflect perceptual learning, and I put this in italics to remind me that I don't know very much about perceptual learning. It's not something I study. It's not an area that I'm on top of, and I don't know the subtleties. But we know very little about the relative roles of factors like initial ability, attention, motivation, and feedback on the depth that we're measuring. So this provides a cautionary note for generalizing to the real world. Experiments in which depth cues are studied in isolation can tell us a great deal about the limits and characteristics of visual processing. And I've done a lot of that work, and I think it's still of great value. However, if we're going to understand how depth information is used under natural conditions, we have to consider the realism of the task and consistency of the depth cues and the experience of the observers. And that, in all cases, we have to take into account the experience that the observer brings. So I would like to thank you for your attention. Oh, wait, my collaborators. There they are. I want to thank my collaborators, in particular in this crowd, Brittany Hartle, who was involved in a lot of the experiments that I talked about today, and also Rob Allison, my longtime collaborator, my funding agencies, and you guys for being here. Thanks.
Thank you very much, Laurie. I want to invite everybody to, you can unmute yourselves and give a big applause for a wonderful talk, and stage is open for questions. I see Julie raised her hand, so you're most welcome to, yeah.
Hey, Julie.
I didn't actually, that was just a wave, but I do have a question.
Sorry.
I do have a question.
I thought.
I was particularly interested in that last set of results, Laurie, the effects of experience. I'm wondering if that is just how object and scenario specific that is. So you've used cylinders with texture, you know, say people had, you probably haven't done this, but it might be nice to try. If you'd started off with people doing, say, the real one with the cylinders, and then had maybe a triangular or different shaped object, would that scaling or the gain of the constancy, or however you want to describe it, would that transfer I'd be interested to know more about that. I think it has quite a lot of implications for training people on very fine scale sorts of tasks.
Mm-hmm. Yeah, no, I agree. And so we haven't, honestly, this is the first time that I've gone through all of, my recent work and really looked at all the experience effects. So, and I'm thinking very carefully about that sort of thing, because the effects are so specific to task and configuration, that it might well be that that you don't even get generalization from one stimulus to another. But I can't say that for sure, because we haven't done it. As you said, yeah, it's not something we would have thought of. Yeah. All?
Yeah.
Laurie, I'm not sure to what degree your various virtual conditions can be regarded as potential Q conflict conditions between disparity and other monocular depth information. As I'm sure you know, there's been a big focus on Q combination, thought of in Bayesian terms of the combining Qs according to their reliability. And I wonder how far the changes you see could be seen as people tweaking those coefficients to make one Q more or less reliable based on their recent experience. And just to put a rider on that, I wonder if your lab experts who spend all their time, their happy time in the lab making disparity judgments, can get to the point where what they've learned is not simply to tweak that balance, but actually to turn off all the other information and just say, okay, this is a disparity experiment. I have a bit of my system which deals with disparity. That's what I'm going to use.
Yeah, I have very, what's the word? I like Bayesian approaches. I like the stochastic models. And I think that the shifting around of weights is a very reasonable way of thinking about this. And in another experiment that Brittany and I did with, again, physical and virtual stimuli, but that doesn't really matter so much. We showed that observers were just switching off or downweighting, almost vetoing motion parallax relative to stereo under the situations that we were presenting the stimuli. So I think it's entirely likely that what you're saying is an explanation. It's just, how do you get at that? That'll be the trick.
Zvi?
Yes, thanks for the talk. I have a question about, like, a general one. Is there any evidence that expertise can affect the susceptibility to visual illusions of depth, like the Ponzo illusion, for example? And you talked about learning 2D cues, and there are some powerful cues there.
I'm not familiar with any evidence of that it would enhance or degrade the percepts from those types of illusions. I know they're very compelling. And I've been collaborating with Erez on some experiments using the version of the Ponzo illusion. That's very compelling. But I don't have anything that would speak to that. Maybe someone else does. Brian might know, but no.
Okay.
Laurie, I want to ask about, you said that you think that this might have to do with perceptual learning, but I want to ask if it's really learning, or maybe it has to do with the fact that there's like task modulations, the fact that you are attending to something and you are investing your resources in a specific, I'm not saying you are ignoring the other cues, but you're enhancing some part of the information. So is there, because it seems that the learning, let's say, or that the improvement is very fast, or was this acquired throughout a few days, or was it like these data, were they within one like day session within one day, or were they acquired along few days or something like that?
So in this last experiment, the test sessions were sometimes on the same day, spread out across the day, but other times across several days. So those are on the order of days in that case.
So have you looked into separate day data, like to check whether there's any, I don't know, changes or improvements?
No, we haven't. We don't have enough of it. I don't think I'm not sure if I gave the number of subjects in that study, but I think we had like 16 observers. And then when I divide them into virtual first and physical first, then we've got like 8 people per group, and it starts to get too sparse to do anything like that. Yeah. But I mean, when I say, perceptual learning, I don't really even know how to think about perceptual learning, because I do think of weighting the information, but the learning could be the process by which you weight, right? And the process by which you weight information may be very short term, or in like task demand based, or it could be very long term because you've learned how to do something like fly a plane and have to land it. It is in some ways not very satisfying to me, because I feel like I haven't given anybody any answers here. I've just raised a lot of questions. But I think Eileen has a question.
Yes, okay, I haven't, sorry about that. Yes.
Oh, that's good. This may be related to the prior question, but what if you bring back your air crew after they've retired? Is that an option? In other words, to see whether whatever they've learned will persist after perhaps years of inactivity? That
would be great. I think it's virtually impossible
to find them.
I don't know who they are or where they went.
They're out there somewhere.
They're out there somewhere, but with age-matched controls, right? Yeah, exactly. But it is, in all seriousness, one could go and access a different population of retired air crew, right? And I just haven't had the wherewithal. That's my phrase lately. I don't have the wherewithal for that. Yeah. Brian.
Laurie, we've talked about this many times in the past, but I do worry that, far too many experiments are still done in incredibly impoverished conditions and unusual stimuli. And in a sense, I could be critical with respect to whether a single line, making a depth discrimination. We do live in a world of surfaces, extended surfaces, and so on, where a lot of the classic problems just simply go away if we had larger displays, real world displays. And I'm going to disagree with Al in the sense that I don't believe we can learn anything from looking at cues in isolation. Going back to the experiments I did with Andrew Glenister and Mark Bradshaw, where we had everything present and then we took away one source of information, and you get a completely different pattern of results that it almost makes no difference. So, I just worry that it's not a criticism of yours, because I think your helicopter experiment is a good attempt to try and do something in a more realistic, more natural situation, but it's still relatively small, the size of the displays and so on and so forth. I just wonder whether we've learned very much over the last, I don't know how many years. Well, I think that,
I'm sympathetic to that view, and I'm becoming more and more sympathetic to that view, Brian, as you know. And so, I really do believe that we've learned a lot about, as I said at the end of the talk, what the capabilities of the neural machinery in terms of, trying isolating information and just, can you even do this? But when you want to understand what's going on in natural environments, I agree that we know very little from our work with these very reduced, reductionist kind of approaches. And one of the ways that we're trying to bridge that or fix it is to do the physical experiments, which take a long time to do, but we've been doing quite a few of them in my lab the last little while, and also use more natural environments, more complex stimuli in displays. And HMDs give you a really good, a nice opportunity to do that. Unfortunately, the resolution, there are still limits in the quality and the controllability. Like it's shocking. You can't calibrate a headset. It's just, so you go with what you got. And so there are a lot of limitations, even geometric limitations, which I'm sure you're aware of, to using HMDs. But they allow you to just throw in motion parallax and render really complex scenes. And so I feel that they're a very nice tool for trying to bridge this divide, if you will. And I know that Jodi's, on board with that, and she's certainly expressed really clearly this approach to understanding vision in the natural setting. So, yay.
Yeah.
If
you don't mind, just as a follow-up, I mean, you concluded by saying that, the role of perceptual learning.
Yeah.
And in a sense, my best guess is, yes, you need learning when you're put in these unnatural situations. If you think about, looking around and asking to make judgments in real world situations, I doubt whether there's going to be some learning, but certainly not as much as when you put people in rather strange environments.
Right. Well, when you have the helicopter, the air crew were certainly learning to attend to, if you will, I think that's what they're doing, attending to monocular information, 2D depth information. Interestingly, I didn't mention this in the presentation, but there's an element to that data which is kind of cool, and that is that, that the condition with the runway line, we told them you can't use the width of the runway line because we randomized it from trial to trial. But you may have noticed that their data for the runway condition had huge variability. And it was because they could not use it. They just were compelled to use that information. And that's something I really wanted to pursue, but we couldn't get access to that group again. But yeah, I think there's learning, there's attention. I don't know how to cut the swath, go through what the right path through that is, but I'm thinking about it.
Thank you.
Laurie, I have another question, and it relates to the actual task. Most of the tasks you've shown involve estimation of depth, or giving some absolute number, let's say, or a relative number. But I wanted to ask, if you were to change the task, let's say, to ask people to judge if one thing was a bit more or less than the other, like comparisons. Do you think people would be more precise across different depth values, or do you think you would see similar effects for things that are that have small depth values versus longer ones?
Yeah, this paradigm issue is a tricky one, because that is an option to do like 2 interval comparisons or even simultaneous comparisons. But in those situations, people can match disparity so that you're not really measuring then how much depth they see. So in some ways, it's very hard. It's not easy to get at how much depth someone is seeing, and avoiding the situation in which they can just say with a probe stimulus, right? You could say, oh, well, how much, tell me what the depth of this object is relative to that using a probe. But they're very, very precise because all they have to do is minimize the disparity difference between the probe and the target. And that doesn't actually tell you anything about how much depth they see between the two. So that's the kind of paradigm problem that we're constantly trying to avoid. And there's a hint of that when you do comparing intervals, because you could, if you don't devise the experiment really carefully, compare disparities. So that's the conundrum.
Okay, I didn't think about that aspect. Yeah. Okay, thank you very much for this very inspiring and interesting talk. And
thank you.
We'll see where all these results are lead. So thank you for joining us. Have a warm winter over there.
Yeah.
And I
definitely.
Definitely hope to see you here more all of you in our next sessions. We are not going to take a big break during the winter holidays, and I'm hoping to get to VSS.
Yay, please come to VSS every
Yes, definitely.
Thanks, Jeff. It's good to see everybody. Thanks for coming, Josh. Nice to see you sitting there.
Yeah, okay. For some reason I couldn't raise my hand because I was. I just wanted. Can I just say I really like that, Laurie? I mean, this is obvious to everyone but me, but it's natural versus virtual isn't the issue. It's how much experience the participant has had at the task, and there are some natural tasks that a lot of people have had no experience with.
Yeah. There's lots of ways to slice this. And I'm glad that the talk went okay.
Perfect.
Okay. We'll see you, everybody. Have a great day.
Bye, Laurie. Thanks for the talk.
Thanks so much. Bye-bye.
Bye-bye.